introduce Viviana Acquaviva. Viviana is a faculty member at City Tech, one of the CUNY campuses in Brooklyn. She's worked on actually I should point out she's coming to us today from Barcelona, where she's spending perhaps a slightly longer sabbatical than originally intended. She's worked on a wide variety of problems in astrophysics and cosmology. She earlier in her career did what one might think of as more traditional pencil and paper theory, trying to understand problems related to inflation and signatures in fluctuations in density in the early universe. And then somewhere around a decade ago, she dived into the world of much bigger data, and since then has been involved in a number of different problems, analyzing surveys, building tools, some of which have been very widely distributed. And so it fits in this sequence of lectures that we've been having on the structure of models, on machine learning, and now looking at the challenges of the universe on the large scale. So, Viviana.
Well, thank you so much, Phil, for the introduction. It's really great to be here. Can you confirm that you can hear me okay? Okay, see, that's, there are, I guess, like nice things in having these remote conferences. So for me, it would have been impossible to join you otherwise. And so, yes, this has been, I don't know if I would say slightly longer sabbatical than expected, definitely quite a bit weirder. But, like being able to participate in things like this is really one of the highlights of this strange year. So let's see. Let me see. Okay. All right, so I titled this session, Big Universe, Big Data, Emerging Challenges in Astrophysics. And so we'll try to tell you a little bit about how I feel like the whole concept of what being a scientist, but being an astrophysicist in particular, has changed through the last decade. And just to give you some practical information, so what I'm planning to cover today is a mini primer of cosmology, just so you can know, where we stand as cosmologists when we look at the universe out there. And I'll talk a little bit about the revolution that data science has brought to Astro. And then tomorrow, I'll go a little bit more in detail on a problem that I've been working on, in different ways for, about a decade now, which is how to measure the physical properties of galaxies. And both the slides with the links to, like different projects and information, and the video, I think, of these lectures will be posted. Now again, on practical details, I think by now you guys are actually more expert about this format than I am. And so, like you should obviously feel free not to use video at all. For questions, I think we have several possibilities. I'm going to ask you to use the chat just because I feel like this is probably the one that's going to be a bit easier for me to keep an eye on. But, I'll do my best in sort of like reacting to stimuli on the screen. And I'll try to answer the questions if I can in real time. If not, I'll try to periodically stop and review. And we also have some like allocated slots, so in case I miss something. And I know that many of my co-hosts here today can help if I miss something important. And of course, it would be nice to have broad participation. And so if possible, I'll try to give preference when answering questions to people who are asking something for the first time. But by all means, feel free to ask multiple questions. I mean, participation is always great. And so as a tentative schedule, I would say I would probably be like blurbing for about 45 minutes now, and then we can take a 10 minutes break and come back maybe with a shorter question and answer session. And then I'll talk some more, and then we're gonna have another Q&A. And we can adjust a little bit as we go, but this is so far what I'm planning to do. Okay, I'll say a few more words about me. So as you heard, well, I'm an associate professor at City Tech, which is, it's the familiar name for the New York City College of Technology, one of 23 campuses that CUNY has, and this one is in Brooklyn. Well, you probably have figured out that I'm from Italy. I'm from a place called Lecce, which is the hill of the booth. And it's known for, well, I would say in order, beautiful architecture. They call it the Florence of the South, beautiful beaches, and amazing food. I think of myself as an improbable astrophysicist. The reason for this is that I feel like most people working in this field would tell you that since they were little kids, they've been incredibly fascinated with the night sky and they could be found outside with their telescope. And I never did such a thing. In fact, I think the first time I took a class out with a telescope, I put my eye on the wrong end. And I have made peace with the fact that, you know, you can be a scientist with many shapes and forms. And I guess another thing that is relevant for this is that even if I'm at a point in my career where I feel like, you know, I've been working in this for quite a long time, but I still feel a bit afraid of commitment, and you know, I still wonder about whether I could be doing something else, or you know, I feel like I'm terribly interested in other things that are not astronomy. And again, I think that I struggled for a long time in understanding that this is okay, that you know, we don't need to have a single narrative of what it means to be a scientist, or you know, like why and how we can become scientists. And so that's why I'm putting it out there. And then I guess, you know, a lot of my thoughts in general on life are also shaped by the fact that I'm a mom to this beautiful girl. She's called Clara. She's now 4, so a little bit older than when this picture was taken. And I thought I would tell you a little bit also about the stuff that I worked on, something that Bill has mentioned already. And here you can see the sort of like zigzagging that I was telling you about. So for my master thesis, I was working on super early universe stuff. So, you know, we're talking about the first fraction of a second, a period called inflation. And then for my PhD, I looked at gravitational lensing in the context of different theories of dark energy and gravity. And I continued this a little bit through my first postdoc. Then I started working on parameter estimation for the cosmic microwave background, which is still early universe, but you know, like not a fraction of a second, more like 400,000 years. And then I started studying galaxies and their physical properties from my second postdoc, and then all the way through my career as faculty. And in the last, I would say, 6 or 7 years, I became more interested in machine learning and you know how it can be applied to astronomy. And I've also thought a lot about you know what's the best way of training modern physicists, or you know how you know for a student who decides to go into a physics career today, how this needs absolutely to mean not just academia but also industry, and you know like as instructors, what are our responsibilities in adapting the curriculum to the needs of you know a modern physicist, not the one of you know 20, 30, 40, 50, 100, 400, 500 years ago. Okay. Now, I thought that, you know, as an icebreaker, we can have a little pop quiz. And so I'm going to ask Gyun if she can launch this. Oh, no, we decided, sorry, apparently I can do this myself. Never mind. I will launch this poll. Let's do it. It has 5 questions, and feel free to answer as soon as you see it on screen. So the first question, I will read it for you. Says, happy to see you, what brings you here? And you can choose between, I'm really interested in astronomy and data science. I've been locked inside for months and watched every show on Netflix. My advisor told me I should be here, or I thought this was an astrology class. Can you see the poll on screen?
Yes.
Okay. Because I see, don't be shy. It's anonymous, by the way, so I will never know what you answer. Question number 2, how old is the universe? And possible choices are 238 million years, 4.5 billion years, 13.8 billion years, or infinitely old. Question number 3, how many galaxies are in the universe? About 200 million, about 4.5 billions, 13.8 billions or 200 billions. Nice. I'll keep going and reading, but then it'll also give you some more time. Remember, there is no grade and it's anonymous. What is the universe doing at the moment? Shrinking, just like planet Mercury, expanding at constant speed. It's expanding but slowing down in its expansion because gravity, or is expanding at accelerated rate because why not? And finally, who gave essential contributions to the discovery of dark matter? Edwin Hubble, Carl Sagan, Vera Rubin, or Chuck Norris? All right, I'm gonna wait a little bit more since I see that so far about 70% of participants have voted, but numbers are really going up. 76%. Let's see if you can get it to 90. Yes. Cool. You know, something interesting that is happening on my screen is that the percentages of the poll don't add up to 100. Show us the results. Yes, we'll do soon. Okay, I think I'm gonna end the poll in 5, 4, 3, 2, 1, 0. Okay, and now let's see if I share the results. Hopefully you guys should be able to see what is going on. All right, now you can see why I was looking at these, and you can see that the percentages don't add up to 100%. So it's a little, oh, thank you. Thank you to Nicholas, who told me that you can select multiple answers. I hadn't realized this. Okay, so happy news for us. Most people here chose at least as their primary reason that they're really interested in astronomy and data. Now let's see, how old is the universe? There's a preference for 14 billion years, but 4.5 billion is also somewhat popular answers. How many galaxies are in the universe? This is probably one with the largest dispersion, so preference goes to 200 billions, but 4.5 billion and 200 million galaxies are also popular choices. What is the universe doing at the moment? And I think the most popular answer is expanding at an accelerated rate, followed by expanding but slowing down because of gravity, expanding at constant speed. So I guess we seem to have an agreement that the universe is expanding. And the correct answers, well, you know, for the correct answers, you can, you probably will have to wait until the end of a lecture, but I promise you will leave all with correct answers. I just want to say, it seems strange that we're shrinking just like a planet Mercury. And so, yes, I can tell you that the universe is not shrinking, but planet Mercury is shrinking. Don't forget physicists, like, fair enough. I've done a little bit of that as well. And then finally, I'm very sad that the contribution of Chuck Norris is not more recognized, but in terms of the discovery of dark matter, we also have almost a tie between Edwin Hubble and Vera Rubin, and then Carl Sagan also has some popularity. Okay, so let's see. I'm gonna tell you all the answers, I promise. Just, you know, you have to wait until this is over. All right, I'm going to stop sharing the poll results. And bye. And let's see. And I'm going to dive into a tiny cosmology primer. So this is something that I always show. I feel like in all the talks that I give, it's almost impossible for me not to talk about these things, which is very simple, but I figure quite mind-blowing. And it's the fact that if we go with the telescope and we look at the closest star, which is the sun, and of course we do this with special filters and special glasses, we see photons coming from the sun The sun is about 150 million kilometers away. And, the nature gave us something really interesting in the speed of light, which is the fact that it's constant. And so if we want to calculate the time travel of light from the sun, we can just use the formula distance divided by velocity, and we get a little over 8 minutes. So we know that when we look at the sun, we look at a picture which is 8 minutes old. But we can do the same thing for other things, for example, with the Andromeda galaxy, which happens to be at a much higher distance of about 2.5 million light years. And this distance is exactly then, these units were completely made up by astronomers, of course, just so we can use light travel time as a unit of distance. And so when we calculate the travel time from the Andromeda galaxy to us, we conveniently find 2.5 million years. And so this means that when we look at Andromeda, we're looking at a picture that is now 2.5 million years old, which, you can view this as annoying, I guess, right? If you typically, when you take pictures, you don't want these like stale pictures, which are like old news now and anything else could have happened. But I feel like it gives us the best and coolest thing ever, which is the fact that as astronomers, we can look back in time. And I think that, this sort of like makes up for all the other issues that we have to deal with in an experimental science, such as the fact that we have only one universe, so we can never like replicate experiments. We can basically have zero interesting experiments in the lab. We cannot make stars, we cannot make galaxies, we cannot simulate any of this. But I feel that the fact that we can actually look back in time is just worth all the other issues. And I like to think about it actually the other way, right? So say I found this nice picture of this galaxy called NGC 2986, is about 100 million light years away. And so if at this very moment in this galaxy, we had astronomers and they were pointing their telescopes at us, what would they be seeing? Let's see, first person who writes it in the chat. If from a galaxy 100 million light years away, right now, someone points a telescope at us, what would they be seeing? Nice, very nice, yes. I think I'm gonna go with the first. I told you that, I was influenced by my 4-year-old. So to me, the fact that they will be seeing dinosaurs at this very moment is just super funny and cool. So of course, as scientists, and congrats to Mayank in the chat. And I think that the Pangea is also a possible answer. Now, as scientists, we use this all the time because it really means that if we're able to build telescopes that are powerful enough to look very far away, then we can basically observe the history of the universe. So in this little chat here, you see, a little timeline of how astronomers have been able to look farther and farther away, which means farther and farther in the history of the universe. And so until the 90s, all observatories were ground-based. And ground-based astronomy is amazing, but has issues such as the presence of the atmosphere, which makes things difficult, at least at some wavelengths. And then you also have like weather and the fact that basically you can also only observe at night. But still, we were able to look at things that were observed up to 6 billion years ago. And this probably is telling you something already about the age of the universe. And then in 1995, we launched the Hubble Space Telescope, a 2.5 meter reflecting telescope that is orbiting around the Earth once every 19 minutes. And you can see that this has allowed us to push the barrier of the oldest object, I shouldn't call it the oldest, but the farthest object ever observed, farther and farther. And then you will also notice that basically, if you look at the instrument from 1995 to 2004, 2010, nothing changing. This is still the Hubble. So the reason for that is that it's very difficult to put telescopes in space and very expensive. So once you have like a great machine that is working, you really want to use it as much as you can. But telescopes are basically just like buckets. to collect photons. And so there's two ways in which you can collect photons or more photons. You can make larger primary mirrors, but of course, like it's difficult to make very large amounts that are also free from impurities, or you can prolong your exposure times. A bit like, if you're taking a picture at night, or if you want to take a picture of fireworks, you need to use a longer exposure. Because just, if you wait a longer time, then, photons will come through the telescope. And so even things that are very faint will start to appear. So this is what we did. We created these so-called deep fields. And basically we kept the Hubble Space Telescope pointing at these like tiny patches of the sky for like millions of seconds overall. And through this process, we've been able to observe almost the entire history of the universe. So what did we discover? Well, I guess this is not like a Hubble discovery, but something that we have certainly solidified in time. And so all faraway galaxies are moving away from us. How do we know? Right, in the end, even if we can look back in time, when we look at the galaxy, we can calculate how far away it is, possibly in some ways, but it's not like we see it moving. So the reason, or the way we know this, is that we have observed this so-called Doppler effect. Now, the Doppler effect is something that I'm sure, since you're all physicists, you've heard about, and usually we think about it for sound, right? And so it's the fact that if there is relative motion between the source and observer, the frequency of any wave that is emitted by the source will change as a result of this relative motion. So for sound, this is something that is very easy to notice. So I put this here that has the horn of a car, and so we're used to this. We're used to this with ambulances or trains. For light, it's a lot less obvious, right? It's not like when you're looking at the headlights of a car, you see the color, which is like, a tracer of light frequency, change as the car approaches you or moves away. However, the whole point is that the shift, right, the size of the shift depends on the relative ratio between the velocity between source and observer and the original velocity of the wave. So the fact that lights travel about 1 million times faster than sound means that on Earth, we're basically never exposed to speeds that make this effect sizable. In space, however, things are moving really fast, even compared to the speed of light. And so we actually observe this change in the frequency of light due to the motion of galaxies. And because in general, things are, as I mentioned, moving away from us, this means that we observe this shift as a shift towards longer wavelength. And because of that, we call it redshift. Now again, the actual way we observe this is not really that we see galaxies changing colors or we see galaxies becoming red, but because it doesn't happen in real time and because we don't know what their original colors are. And so even if we look at a galaxy and we say it's redshift, it's a reddish, we don't know if this is the effect of redshift or if it's just, like these are the stars that it contains. But we do have access to this measurement through something very simple, which are the emission spectra of elements, and in particular hydrogen. Hydrogen is very popular in the universe, like, unlike, for example, like on Earth, it makes up about 90% of all matter. So it's just like extremely abundant. And so if we look at something like the spectrum of hydrogen, we do have something very well known to compare it with, which is, how the spectrum will like if measured in the lab. And the fact that we see like all these lines shifted tells us two things. One, all the emission lines are shifted towards the red, which means like all these objects are moving away from us. And two, the further away objects, typically I'm talking about galaxies, are, the faster they're moving away from us. So this is how we know that all galaxies are moving away. Now, what's the reason for that? Well, I guess, when this was first found, physicists thought, okay, there must be some reason why nobody likes us and galaxies are running away. But you see, if you take a look at the history of astronomy, it's a very humbling history, right? Aristarchus he's actually one of my favorite scientists of all times, because he had basically thought about lots of things, including the fact that the Earth is round, and proposing a heliocentric model, even calculating the distances of other planets. And like he was the first one to say, hey, like there's really nothing centric about our location. Copernicus, of course, popularized this heliocentric model. Then Herschel, a few centuries later, he mapped the Milky Way galaxy. It didn't, do an amazing job just because he didn't know about cosmic dust. So he tried to do this counting stars, but it's another story. But still, he found that we're not at the center of the Milky Way galaxy. And then Hubble, which is the one on the right who looks like an actor, in my opinion, he found other galaxies other than the Milky Way. So I feel like the whole history of astronomy suggests that there is nothing special about us, and there is nothing special about our location. And so this idea that galaxies should be running away from us in particular is very hard to reconcile with everything else that we have learned. And so because of this, the alternative that was frankly incredibly hard to accept, even for someone like Einstein, that like was no stranger to new concept, is the fact that space itself is expanding. And so in this case, if you look at galaxies like the blue dots of this picture in the left, and then after some time you can see them as the red dots of the picture in the right. And so no matter where you are in the universe, so for example, let's assume that we're here on this second dot, second row, second column, after some time, you will see that all galaxies have moved away, and of course your location is the only one that stayed the same between A and C. And so you will see that all galaxies are moving away from you, but this is common to any location on this map. So for example, here you see the same thing, but assuming that you are in the top left dot. And actually, just this simple explanation is also able to explain the other things, not just why we see all galaxies moving away, but also the fact that the farther they are, the faster they move. And if you're willing to take a ruler, you could check this for yourself. But basically, if you look at two galaxies that were close in the first picture, say that they were like one little horizontal distance unit away, and like they have moved by a little bit, right? So the distances has increased by a bit. And if you look at the distance between galaxies that were separated by two little units of distance, now they have moved away by this amount, which is more. This all happens at the same time. So this tells you that the one that was farther has been moving faster. Do I have telescope data to show the faster distances of galaxies? That's a great question. I guess not in real time, because this is not what happens in real time. But the redshift that we measure measures the speed, and distances is something that, so if you have another way of measuring distances, which is something I will also touch upon, then you can compare this distance to the redshift that are measuring and seeing the linear relationship between these two quantities. Okay, so we have concluded that the universe is expanding. Hopefully you guys are all convinced, and I guess you were already based on the poll results. And I feel like that, just from this very simple assumption, you can also say, okay, if the universe has been expanding for its entire history, then I can rewind time. And as I go back in time, I get to a point where the universe is smaller, 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 and you get to a point. And this means that the universe is not infinite in time. You need to assume that it had a temporal beginning, which is, again, something that we are used to think of right now, but I feel like, again, it was something quite difficult to accept. And so this temporal beginning of the universe is what we call the Big Bang. And so the whole Big Bang theory is really a collection of some very simple facts that can be derived by the fact that the universe is expanding. So first of all, the universe is finite in time. And so this initial point is what we call the Big Bang. And there's really not necessarily an explosion associated to it. What you need is something that provides momentum for this explosion. But in general, it's just like a time where the universe was very hot and very dense. So in space, is the universe finite or not? Well, this is a bigger question. And I think it's easier to think about the observable universe, which is basically like the size of the space that light could have traveled between the beginning of the universe, the Big Bang, and today. And finally, there is no center and no edge to the Hubble expansion. In other words, all observers in any galaxies anywhere in the universe would be measuring exactly the same expansion of the universe. Okay, so I'm gonna read this question in the chat, which says, at what decimal point will we need the accuracy of our distance to be able to detect the change in distances in galaxy within, let's say, an exposure time of 10 years? Well, I think, it's a very interesting question. It's not an easy one because, like my instinct is to say we are not going to be able to see galaxy distances change in real time almost ever. Like, we can do this with stars, but it's already incredibly difficult. But I'd be willing to, try a pen and paper to sort of calculate in 10 years time what would be the fractional change in the distance of a galaxy. Of course, it depends on what redshift the galaxy is, just for fun and to see how far we are from now. I cannot do it in real time, but I'll try to remember to do it tonight so I can get back to you tomorrow. And then, since you're here, I have another question. The universe. Oh, very nice, very nice. Well, I don't think there is a maximum limit for expanding. In fact, I think that the most popular theory for the end of the universe is something called the heat death. Katie Mack has a book coming up soon about the end of the universe that is actually available for pre-order. But I think, I always feel that we are lucky to be alive now because we can look at such a variety of objects. And I think, in a few billion years from now, the expansion of the universe will have proceeded so much. I don't know exactly, we have proceeded so much that the sky will be a lot less interesting than it is today. Can I type the book title in the chat? I don't remember the exact title, but if you Google Katie Mack and then book, then it should come up right away. Okay, let me continue on this to tell you about the age of the universe. And this is just because, you can make complicated models, but actually, okay, thank you. But actually, I feel like that even with, few data, you can have a pretty good calculation of the age of the universe. So we said that the farther away galaxies are, the faster they're moving away. And this means that if for a bunch of galaxies, you're able to measure both their distance with some method and their velocity, and you put it on a graph, then you can get basically the rate of expansion as the slope of this line. And then you can also think the following thing. If at time zero, at the Big Bang, all galaxies were exactly in one point, and now, today, all galaxies are at a certain distance from us, then basically, the speed of the expansion is given by 1 over, so actually the speed of expansion is the y-axis of this graph, and the distance is what they say on the x-axis. And you can think of the age of the universe as the time that is taken for the galaxies moving at a certain velocity v to reach their today's distance d. And you know, like the d and v, the distance velocity pair, are of course different for each galaxy, but the time is the same. And so basically, if you calculate the time as distance divided by velocity, as 1 over h naught, you get a value of 14 gigayear, which is actually very, very close to the best estimate that we have today. It is a little bit by coincidence because, you know, the validity of this law implies that the expansion has proceeded at constant speed, which is actually not the case. But there is a compensation effect that we will see in a little bit. And so in the end, this simple calculation gives a pretty spot-on estimate for the age of the universe. Okay. This is it for cosmology. We also found another bunch of interesting things. For example, we found a galaxy called GNZ11, which is the farthest object we have ever seen galaxy-wise, and it was observed only 200 million years after the Big Bang. And this is not only interesting because we can see so far back in the past, but also because, to be honest with you, we don't really know how it is possible that a galaxy already existed such a short amount of time after the Big Bang. So this was like very cute as a baby universe thing, but also something that leaves us very puzzled. We've learned that galaxies can change shape, and in particular, they tend to go from from spiral shapes to elliptical shapes. And the way they do that is by colliding. And so here you see like a picture of two galaxies in the act of colliding. And of course, we cannot see the whole merger in real time, but you know, like we can get a sense of how the shapes of galaxies change by looking at different slices at different distances, which means like, you know, a different snapshot of the universe, and seeing how overall the population of galaxies tend to change. And finally, as I promised, you know, you will have to have all the answer. I'll get back to you on the question. And so we learned that there are about 200 billion galaxies in the universe. And, you know, each galaxy can contain a few 100 billion stars. So I don't know. I mean, it's definitely something that makes you feel small, right? When you compare the size of our own universe and everything we've always cared about, and, you know, how it's, you know, they probably will lie in, you know, a few square miles here and there. So it is something. But I guess, you know, being exposed to the beauty of the universe, makes it worth it. Okay, I'm gonna look at a couple more questions. How do you know it was a galaxy, the Z11 object? Very good question. I think the reason is that it can't be anything else. Just to be visible at those wavelengths, it needs to be like a large agglomerate of stars, something large enough to be called a galaxy. And I mean, we don't really have like, you know, a great spectrum, but, you know, like its spectral shape is compatible with other galaxies observed at very high, although not quite as high redshift. And then look, we have a question. How do we know this? How do we know that there are 200 billion galaxies? Was this the question? I hope so. Okay, great. Yes, well, I guess that the way we know this is that there are small areas of the sky that we have observed in such great detail that we are confident we can count the total number of galaxies there. It's possible that we are missing the ones that are, you know, like very far and therefore very faint. But overall, just because of, you know, how galaxy formation proceeds, we can assume that the fraction of these galaxies that we're missing is fairly small. And so because we also believe that, at least on large scale, the universe is homogeneous and isotropic. And so basically that observing one patch of the sky versus another patch of the sky on average gives you the same result. then we can literally like, count galaxies in a small piece and, like count how many of these patches we have in the entire sky. And this is how you can get this estimate. All right, and actually I want to show you something that, yes, for the observable universe. So I want to show you this video, which is a real flyback through galaxies. So I mentioned that there are some patches of the sky that we know really well. And so one of them is the Hubble Ultra Deep Field. We have like 2 million seconds of observations. And so what NASA astronomers did here is start from the picture, and every speck here is a galaxy, and then calculate galaxies calculate distances for all these galaxies so that we actually can, turn a picture into like a 3D picture, and then sort of like fly through. So this looks like a simulations, but it's actually all real data. The only thing that, is measured as opposed to observed is the distance of the galaxies. But this is something that we are kind of confident in. So of course, now we're going back in time towards the Big Bang, and you can see that there are some like really massive objects still for which we have some detail, but a lot of things tend to become smaller. They also tend to become bluer because younger stellar populations tend to be dominated by the color blue. And at some point, you're going so far back that you don't really see anything. And so here's where we could be missing some galaxies from the count, but we think that the overall fraction would be small. And let's see, if we know the galaxy can collide, then eventually the number of galaxies reduce. Yes, I think this is an excellent question. And I think the answer to this is yes. And this happens for various reasons. Like by itself, I guess that the total number depends on the balance of how many new galaxies are formed versus the galaxies that are colliding with each other. But because of this expansion of the universe, and as we will see, it's a pretty powerful one, then the rate of formation of new galaxies is lower than the one that we reduce by mergers. And so yes, in the far future, we'll have fewer of them. They will be more massive than now, and they will tend to be of elliptical shape, because ellipticals is what happens when you destroy all the order angular momentum of spiral galaxies in the collision process. Okay, I'm liking this interaction. I hope you guys can make sense of like my talk and my attempt to answer the questions. So now that I showed you like the only pretty video that I have, I'm going to tell you about all the stuff that we don't know. So we said, okay, our main prediction is that the universe has been expanding. This is the Big Bang theory. Now, of course, you could ask, okay, but why is it expanding? What sort of like powered this expansion? And I guess, I don't really have an answer for this, but in general, when you think about the dynamics of the universe, you think that there are like two forces that are competing. One is the sort of like, momentum or pressure from the expansion, and the other one is gravity. This is like, pulling back. And so the balance between these two will tell us the rate of expansion. So now, can you predict what happens if I put more or less matter? Or actually, let me formulate it a little bit better. I will look at the first 5 answers in the chat to make a poll. So the more matter in the universe, the more its expansion will A, slow down, or B, accelerate. Please vote in the chat so I can look at 5 of them and make it a poll. If I put more matter in the universe, what will happen to the expansion? Will it accelerate or will it slow down? Okay, who? Okay, let me see. Okay, I'm gonna close it now. Okay, so let's see. I have Okay, B, A, 2. 4B, 4A. Okay, up to here I have 4 and 4, and then wow, I have like 4 more A's, 4 more A's. Okay, I don't know if this is confirmation bias or what, but I started with like like almost a tie, and then I think like A has become the answer of choice. And so in this case, yeah, if I have more matter in the universe, its expansion will slow down, right? You know, the more matter I put, the more the expansion will slow down because, you know, the more gravity I will have to pull back against this initial pressure. And so this is nice because astronomers thought, you know what, there's a lot of things that we cannot observe, but one thing that we can do is that we can weigh the universe by measuring how big it is. Now, this is not a simple process. And the reason for that is that when you go out and look at the sky, say you see a star, you know, you say, okay, I can measure how bright it is. I'm going to write it somewhere. Then you can go, maybe you find another star and it's closer, but also smaller. But it may, you know, because of the combination of these two things, it may end up having the same brightness. And then same thing with something that is maybe like, you know, bigger and more luminous, but also farther away. When we look at the sky, the brightness that we measure is the product of the combination of two things, not just their luminosity, but also how far away they are. And so just measuring this brightness is not enough to know the distance. However, if you had light bulbs instead of stars, now you can see that you could trust this process, right? Because if you know that the objects you're looking at all emit the same amount of energy, then you can trust that the dimmer ones must be dimmer because they are farther away, not because they really are dimmer. So the question is, do we have something like that at the astronomical level? And of course, I'm telling you the answer is yes. And the brightest ones that we have are something called type 1a supernova. These are explosions, and the supernova in general can be the explosion over massive stars or a white dwarf star. The nice thing is that they're really bright. In fact, they can be as bright as an entire galaxy for, you know, a period of days or even weeks. But why is it special? And the special thing is that this type 1a all share the same birth process, which means that they all come to explode as a result of the fact that a white dwarf star, which is like a really weird object sustained by electron degeneracy pressure, gets to a certain mass limit. And at this mass limit, the law of quantum mechanics tells it that it cannot exist. And so it explodes. And because they all go through the same birth process, this explosion happens when they all have the same mass. And because they have the same mass, then they have the same luminosity. Now, to be honest with you, it's not that their light curves, light emission with time, are exactly the same as you can see here, but we are going to pretend that we can standardize them. And so in the end, you can bring them about to the plot on the bottom right, which is when they are all lying on the nice same curve. So if you can find these objects, you can use them as astronomical standard candles. That's what we like to call them. So astronomers did that, and they measured distances to a whole bunch of type 1a supernova, and they found that they were all dimmer than expected. And now this is a way of measuring distance that doesn't depend on redshift. So it's really a test of your cosmological model. And they found that, you know, they all, based on, you know, the amount of matter that we found in the universe, they were all expected to be found here, and all of them were quite a bit farther than the expectation was. And this was a big shock. In fact, I really used to like the version of the Hubble website that had the original response to these discoveries. It was very 80s. It had like this ambient music where people read these things like a reasonable position for someone to take is that the observations are wrong. But unfortunately, it's been recently modernized, I guess. And so, you know, like now you can see like a lot of nice data, but I really like how it used to appear. And then anyway, the issue was that we don't know of any force that can accelerate the expansion rather than slowing it down. And so, you know, in lack of a better word, we call this thing dark energy. And I think dark energy is really poor choice, unfortunately, of term, because it really should be called invisible energy. There's nothing dark about it. We are the ones who are in the dark about it. And so it's just something that speeds up the expansion, stretching space-time. So perhaps, and this is, you know, like the papers announcing dark energy came out in 1998. So it's been like over 20 years. And unfortunately, I don't think we have a better answer than what we used to have when it was proposed. which is probably our best bet, is something called the cosmological constant, which is a uniform layer of energy that fills space everywhere and perhaps is just like associated with vacuum. And in other type of interaction, we know about vacuum energy. It's just a cosmological constant. It's just there's a very, very wrong amount of it to be compatible with this naive explanation. But in any case, this is something that Einstein had predicted, then rejected because it really had trouble accepting the fact that the universe was not static, but he might have been right. And I won't tell you more about dark energy, unfortunately. You can look at the slide, you can see many, many things that we don't know. And anti-gravity, unfortunately, doesn't work. And then I have also to admit to you that unfortunately, dark energy is not the only problem that I have. This was already about 75% of the total energy budget of the universe. We need a lot of it because it's not that matter has gone away. We still have the matter that is supposed to slow down the expansion. So finding an accelerating expansion means that we need to counteract this effect of matter, and then still pushing towards the opposite sign. So it takes a lot of energy to do that. But then, even if we forget about dark energy for one moment, we also have a problem with matter. And so this is something that was already known in the 30s, but really was solidified in the 60s. So when we look at galaxies, for example, the Andromeda galaxy that you see in the picture here, you can see that most of the visible matter seems to be concentrated in the center, and then the distribution of matter sort of fades away. And so if you measure rotational velocity of stars, how fast stars are going around the center, you expect something that is similar to what happens in the solar system, where most of the mass is in the sun at the center, and the planets that are closer have to move very fast to sort of not fall in, and then planets that are farther away move much slower. But instead, and this was actually Vera Rubin that I was mentioning to you in the beginning, taking this data, if you measure this velocity, for example, for Andromeda galaxy, you see that even stars that are really far out, much farther out, in fact, of the distribution of visible matter, are moving much faster than expected. So this is not in itself a proof that there is invisible matter, but it's certainly something that can be explained by that. But you could also say, okay, I'm not sure. Perhaps what I'm looking at is a different law of gravity. Maybe gravity just becomes stronger in certain circumstances, and so even if I have less matter, it's enough to produce stronger gravitational energy, and because of that, stronger kinetic energy in the stars around the galaxy. Fair enough. Then we saw something like the bullet cluster, and so this is a really interesting objects, because in a bullet cluster, well, it's a cluster of galaxies, so you can see that there's a bunch of galaxies here, and then there is also X-ray gas, X-ray emitting gas. It's some gas that is very hot and so emits in the X-rays, and it's the one in pink. So it's not visible to our eyes, but it's visible to a telescope. So that's all okay, ordinary matter. However, for this particular cluster, we were able to measure its true mass distribution through gravitational lensing, the fact that mass can bend the space-time. And now you can see that there is a displacement. This is traced by the blue. And so you can see that basically the center of mass of this, let's say, two lobed objects. So, if you will, two center of masses are displaced both from the visible matter and the X-ray gas. And this is something that a different theory of gravity has a lot of trouble explaining, because you can imagine the constant of gravity changing, tuning the strength of the interaction, but you cannot make an action at the distance away from where the gravitational potential is. And so this was for a long time considered, this is considered to be the most direct evidence of dark matter that we have. Okay, I'm going to go for a minute about this couple of questions I see. Yes, we could say that Einstein was throwing darts in the dark. I like it. And a different theory of gravity in this sense, yes. Means a different exponent, yes, exactly. Instead of r squared, we could imagine that. That's one possibility. And we can imagine, or maybe another way to look at it is looking at Newton constant rather than a constant as something that can vary with time or with other characteristics, for example, environment or like background density. Okay, I feel like I'm running behind on my schedule, but let me give you a summary and then we can like take a moment. So the universe is really huge and it's been around for about 13.8 billion years. It's been expanding ever since, first slowing down and then accelerating. There are about 200 billion galaxies in the universe. Each of them can have a few hundred billion stars. So overall, we like to say that there are more stars than grains of sand in all the beaches of the Earth. And if you think not just a star, but something like a sun with its own planetary system, I feel like it's even more overwhelming. But anyway, however, all of this stuff makes up for only 5% of the total matter-energy budget of the universe. The remaining 95% is dark, and by dark I really mean invisible or undetectable, if you will. So dark energy and dark matter. And so we have this big issue of how can we learn about these things if we can't observe them. And so this is what I'll try to tell you about in the second part of the talk. So I would say, unless you have some burning question right now, I will propose that we break for 10 minutes. And then if you want to use this time to, like think about more questions, I'm happy to answer at the beginning of next session. And then we'll move on to a different topic. So I'm going to put this. So I'm going to go back to the chat and I'll take a look at the question. So I have a question from Vanessa, which I think is like, the first one from the break, asking, is there any other observational evidence that will point to a Mond-like theory instead of the presence of dark matter? Well, let's see. Up to my knowledge, no, in the sense that I think that MOND, and by the way, for people who may not be familiar with it, MOND stands for Modified Newtonian Dynamics. And so there are theories, as I mentioned, that we're looking at a modification of the Newton's law of gravity as opposed to dark matter as an explanation for some things, among which rotational velocities. And I think the main issue with MOND is that if you calibrate the theory, for example, to explain things like rotational velocity of stars in galaxies, then you miss the opportunity, or you're not able to fit the data coming from, example, from the rotational velocity of galaxies in clusters of galaxies. In other words, I feel like MOND needs to be fine-tuned to environment, but has a lot of issues in trying to fit observation on different scales, so like both distance and densities. And then something like the bullet cluster, where you find the displacement between visible matter and center of gravity, this is something that something like MOND cannot handle very well. So I would say, like as far as I know, no. I mean, I guess we're used to dark matter, but I would also agree that it's a concept that is completely insane. And so, I'm presenting the dark matter as like the sensible alternative, but in reality, I agree that, our bar for accepting it should be really high because it's a really strange form of matter. Oh, sorry. Then Irsadi had a question, which is, how can we measure the center of the universe? And I think like a couple of people who were commenting on this. And I would say that, they're really, I think the way I like to think about it is that there really is no center. And so often we use the analogy of the balloon, and I'm guilty of that as well. But I want to say that I think that the balloon kind of works if you, oh, I'm going so far back just to find this balloon. It's going to take me forever to go back. Where are you, balloon? Okay, here you are. And so I think this works as an analogy if you imagine that you are on the surface of the balloon, right? So if you imagine that the universe, rather than being three-dimensional in space, has two-dimensional, then you bring it down to a two-dimensional space, which is the surface of the balloon, right? And so now you think about yourself not being at the center. Like, forget that there is a third dimension here in this picture. You are on the surface, and for every point on the surface, especially if it's a perfect sphere, not a balloon with a little thingy, every point on the surface is completely equivalent to one another, and you can like walk anywhere in your 2D space without ever encountering an edge, and the distances that you measure to anything else will change in exactly the same way if you're on the surface of the balloon. So I think this works. And now, of course, you have to imagine a three-dimensional balloon, which doesn't work. But I feel it's just that, like, even when we look at the balloon, we see the center of the balloon. And unfortunately, this is not the case. But I think if you think about the surface, then you can think of the observable universe as anything that is like inside the volume of the balloon. And as the balloon expands, then the observable universe, which is, like your light cone in the past, continues expanding. So I hope this helps a little bit in the visualization process. And okay, another, a bunch of interesting questions. So let's see. Can we have interaction between dark energy and dark matter? I mean, I don't think anybody knows. I think, of course, it would be really satisfying to be able to solve both of these problems in a way that is somehow cohesive, right? And so rather than having to come up with two completely different explanations of dark energy and dark matter, which is what, like in most cases we try to do, if we could come up with like one sort of phenomenon that can explain both, or, like even, like I don't know, some form of like interacting fields, it would be really satisfying. But again, to the best of my knowledge, we are very far from this target, and the most promising solutions that we have seems to be actually like of different nature and not interacting. So I also see how optimistic I am that dark matter exists and will be detected. Well, I feel like very bad about this, but there was like a big press conference from the Xenon experiment, which is like an underground experiment searching for direct evidence of dark matter, just a few days ago. And so I think I'm actually quite confident that this will happen. I feel like if dark matter is some of the simplest form, I think that the next decade really will bring something conclusive about this. And the last one, and then I'm going to have to restart. We think in general relativity, is it the same as the speed of information transmission? I would say in the simplest scenario, yes, right? So one of the foundational principle, I think, of general relativity is that nothing can travel faster than light. And so really the speed of light is also the limited speed at which information can be transmitted. But then is this, how fundamental is this concept? This I really don't think I can answer. Like, what possibilities we have if we are willing to relax this assumption. And I guess, we think, or we tend to think, or at least I tend to think, but I think most physicists tend to think as, like mass as energy, as like two forms of the same thing. And so I think of mass as something that, like slows down particles. And so if you think about, a massless particle, then if mass is the only thing that can slow down a particle, then this particle needs to move at the speed of light. And so we think of this for photons, we think of this for gravitons. And so in a way, it will look like, okay, you know, what else can move at superluminal speed if already like the lightest thing ever is moving at the speed of light. But, you know, if you think about it, I feel like, you know, like every decade, every generation in physics brings about so many mistakes that we have made, so many incorrect assumptions, that I feel like it would be really foolish to think that we have already said the last word on this matter. And also, I feel like that as an astronomer, the speed of light is really annoying because it really sort of prevents the possibility of getting in touch with faraway civilization in a time that is compatible with our lifetimes. And so I guess I really hope that the answer is no, that, you know, we will find a way for information to travel superluminal speeds. Yes, and yeah, Amir, okay, last question, then I promise I have to move on, but I really like this question, so I also don't want to. Can we have, yes, in fact, when we talk about the observable universe, this is exactly the horizon that we talk about. We use the fact that the universe has been expanding, and we know, or, you know, like more or less we know at what rate, we know for how long, and we know how fast light has been traveling during this time. When we put these three things together, we get to the maximum distance from the Big Bang that light can travel, and this is about 14 billion years. And this is what we call the observable universe, and this is sort of like the information horizon. So, you know, again, if the speed of light is the limiting factor for, like, you know, the speed of transmission of information, then this also coincides with, you know, like the biggest region that can have been in causal contact, you know, in its interior. Okay. Oh, now I have to scroll all the way. Fast. Ah, lots of animation. La 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 la. Don't you guys enjoy the sound track? Okay. All right. So I was telling you about, you know, like all the things that we don't know and all the issues that we have. And I was, you know, like mentioning the fact that because so little of this is directly observable, how can we learn about it? And then, you know, risking sounding like a broken record, I gotta tell you that the answer is still galaxies. And that's why probably I found something I was willing to work on for more than like 5 minutes. So this is like, you know, another picture. And this is Goods North, another one of these special patches of the sky. There are about 15,000 galaxies in this picture alone. And, you know, this is like almost as large as the Hubble ultra-deep field. So why is that? Well, the reason why galaxies are awesome as universe tracers is that, first of all, you know, we learned that they can contain hundreds of billions of stars, which means that they're very bright. And so if you're looking for something that, you know, is, you know, like a marker that you can see from very far away, then you want something that is quite luminous. Second thing is that, as I mentioned, the first galaxy that we observed was observed only 200 million years after the Big Bang. And so this is just like, you know, a couple of % of the overall life of the universe. And so, you know, if you're looking for something, you know, to measure evolution, then having some markers that have been around for like the vast majority of the life of the universe is very convenient. Third is that, as you heard, we have issues with expansions and we have issues with gravity. And so galaxies are sensitive to both, right? Because, you know, like if you're just looking at where they are and how far away they are, then, you know, like you'll be probing the expansion. But, you know, they're also sensitive to gravity, both in the way they form and the way they evolve and the way they interact with one another. And so you can look at both these aspects. And so in general, looking at how their properties evolve through time, you know, can help us solve a lot of questions in science. And we'll look tomorrow a bit more in detail at some of these. So are we gonna look at galaxies? What plans do we have for this service? And, you know, I want to mention at least one. It's the, you know, like really biggest project in the pipeline that we have, at least for ground-based astronomy. And this is the newly renamed Vera Rubin Observatory. You could have perhaps heard about it as the LSST, the Large Synoptic Survey Telescope. It's an 8-meter telescope that, is already, in like advanced stage of construction. It is on the Cerro Pachón mountain in Chile. And it's been, compared to the usual, it's been like amazing at, like keeping its construction on track. And so we're really looking at, not just science verifications, but full science operation in just like a few years from today. And this will be like, a general operation service in the sense that, it's open to everyone, typically with a competitive process, and data cannot be proprietary. So it's really, something for like whole humanity. Now, let me tell you a little bit about the data that this telescope will bring. So roughly you can think of the data collection ability of the telescope looking at the size of the primary mirror times the field of view, which means, like the area of the sky that can be covered in one observation. And so here you see, like in this picture on the left, you see a little comparison chart of the LSST, still like the old name since the renaming is quite recent compared to others. And look at this, this is like a logarithmic scale. So it's at least a couple of orders of magnitude more than any other service. And overall, it's expected to image a considerable fraction of all galaxies in the universe, right? So the anticipated number is about 20 billion. And so we're looking about 10% of all galaxies. And they will be observed in 6 filters, and it will cover about half, like a little less than half of the entire sky. The entire sky is about 43,000 square degrees. But if you look at the details of this data, then I feel like it's even more mind-blowing. So I put some like red like ovals around here. I think, we already talked about the estimated counts of galaxies for data release 1 through data release 11. And then, like just, we never think about this, but we really have issues with like even like transmitting data, right? Like the location of the telescope is on the summit of a mountain. And so even, like the bandwidth that is needed in order to transmit data first to the base and then to the data processing center, which are in North America, is amazing. And in general, basically, it just as a summary, each night collects about 30 terabytes of data per night of observation, which of course need to be streamed between all these different sites. And every night you expect to have between 1 and 10 million time domain events. And time domain events means something that is happening quickly and may possibly need follow-up. So these need to be detected and transmitted within 60 seconds of observations. And, it is quite a feat. Now, I can tell this like 30 terabytes of data per night. I think that it's useful perhaps to compare this with what other previous generation surveys used to have. And so, like another amazing survey was the Sloan Digital Sky Survey, which is actually still ongoing. But, I looked at the data release from 10 years ago, just to see, like what's the change in 1 decade. And so this is when I do something like I'm gonna try and follow these links, and then I'm gonna try and share the actual screen. So let me see if I can do new share. Okay. Okay. Do you see Sloan data release 7? I hope so.
Yes.
Thank you. And so we can look here, like for the total amount of data in the entire survey, the most advanced survey from exactly 10 years ago. And so the imaging catalog, actually data volume that you can see here for images is, including all the images and then derived data products like, catalogs, max and whatnot, is about 40 terabytes. 60 we want to include also secondary catalogs. Then you also have some data from spectroscopy that overall don't get to the total of 4 terabytes. So the issue that something like the Vera Rubin Observatory will have is solving a data transmission and storage problem every night that is equivalent to the entire data volume of a full multi-year service of just 1 decade earlier. And so these are, the sort of challenges that we have to deal with. And because of that, we had to come up with better ways to store and process data. And, this is what big data is about, but I don't think the main problem is actually size, right? Because I feel like if you're just sort of, like multiplying your data volume, you want to go at it with certain measures. But here we're also really increasing the richness of the data. For example, we are going to have many pictures of the sky that have been taken a different wavelength. These are data that talk to each other, right? So they cannot be processed as independent because they're not independent, and there's a lot of value in being able to put together a coherent picture. And at the same time, we have to prepare for many things that we don't know yet exist, but will be possibly, some of the most interesting aspect of this survey. And this is what I call new data. And this is an actual picture of a real galaxy merger that looks like a question mark. And so it's in dealing with this rich data, I feel like not just the sheer size, that we really have to come up with new method. And let me see these questions. Yes, I agree that, yes, it's not just excellent job creation opportunities, but I think excellent opportunities for international collaborations that I'm really hoping the US won't screw up, and I won't say anything else. And then the energy footprint, well, this is also a very interesting question. Unfortunately, I cannot answer, but I can take a look to see if the answer is readily available somewhere and try to bring it about tomorrow. Okay, so because of, this both size and type of data revolution, then in astronomy, just like in about any other field, we have been talking a lot about machine learning lately. And so to me, I feel like, if I had to define what machine learning is, which happens quite often since I teach it, I like to think about it as the art of teaching a machine to make decisions. And I think you guys had an excellent primer from David last week. So I hope I won't repeat too many things. But in general, I think, in general, you're trying to do one of these four things. You're trying to recognize things. For example, cats and dogs. I feel like, you're not even an astronomer if you don't put cats and dogs in your machine learning slides. Or you may be trying to predict things, you have some information, but some of it is missing, and you're trying to fill in this gap. Or you're trying to group together things that are similar. Or finally, you're trying to simplify things. This is actually something that is less talked about, but I think for us, one of the most fundamental, because it really amounts to, what's the most essential way in which you can relay information about an object? What makes a galaxy, what makes a star, if you have to describe it and recognize it. So I want to tell you a little bit about, what we use machine learning for in astronomy. Of course, it won't be a complete list, but, hopefully it gives you, some general sense of what we like to do. So the first thing, and this is, again, because of just the size of the universe and the amount of data that we have to deal with, is save time. So here we're not trying to do something better than humans or, better than other algorithms that we have. We just don't have the resources for this. So one of these problems, perhaps the first that machine learning was consistently applied to, is recognizing galaxy morphologies, whether you're looking at a spiral galaxy, an elliptical galaxy, and a regular galaxy, a merger, and so on. So for humans, it's actually quite easy to do, much easier than for a machine. But if you have millions or even billions of objects, clearly you cannot afford this. And so one very helpful step was harnessing the power of citizen science, which is, you can ask a lot of people to look at a few of this image, and then you can use the principle of majority voting that actually tells you that even if a single person is not right all the times, when you stack together the majority opinions, then you are much more likely to have a reliable classification. And then the other possibility, of course, is to have automated classification with machine learning. And so use, like a subset of objects for which the morphology have been humanly classified to train a machine to do the same thing. So this is actually something that has been quite successful. Another thing that I really like is being able to make model-free inference. And I like to think of this as galaxies are not spheres. So the alternative approach, if you will, to measuring things in astronomy is to make models of objects. But the problem is that we are modeling things that are very complicated, like galaxies, with a handful of parameters, like 4 or 5. And so this means, this is not wrong in itself, because of course we cannot, study a galaxy as a dynamical system of all of its single constituents. But, there is a bias introduced by the fact that we choose which parameters we think are important. And so, for example, say that from the spectrum that you see here on the left, you want to calculate something about the galaxy, to measure something about the galaxy, for example, like the redshift, which is, as we've learned, proportional to the distance. Well, you can do so by writing a likelihood, which means that you need to write a model of how this galaxy, how this spectrum that you observe, in fact, will look like as a function of all the properties that you think are important about the galaxy. For example, the mass, the star formation history, the dust, the content in metals, and the redshift. And so this is a very powerful process, but really it depends a lot on whether what you wrote is correct. And in general, you choose functional forms for these things in order to simplify your mathematics a little bit. However, if you are able to have this information for a bunch of galaxies that you can use as your training set, then having something like a neural network as your relationship between input and output gives you a chance to use much more complicated models and also much more data-driven models. So rather than being you, the scientist, choosing which 5 numbers are most important, this could be emerging from data. And this is very nice. And so you can capture complex relationship without having to explicitly write down a model or a likelihood. Then this is, again, one of my favorite things, because I like things simple. It's much easier to use higher level data products, for example, images. So you see here, say that I'm studying this galaxy and I want to learn something about it. If I were to write a model for it, I have information in every single pixel. But writing, sort of the probability that I would, observe data in a certain way, given each pixel in this image, is a very complicated thing to write. But there are several machine learning algorithms that are actually meant to be there, and to be fed high-level data progress such as images, and one bat an eye at the process. And finally, it may help us making problems more tractable. One way of doing so is with dimensionality reduction. And so you can see here that, you have this little s, which is a 3-dimensional space, but, the property of color is only existing on a 2-dimensional manifold. And so you can find a smart way of reducing the dimensionality of your data to 2. And here, these have different degrees of success, but the 2 on the bottom row are better than the one on the top right. And so this means that now, you can achieve compression in your data set without losing a lot of information. And as you can imagine, this is quite essential for us astronomers. And the other thing is knowledge transfer, or if you prefer, domain adaptation. So the fact that because things are, for example, running large simulation of the universe is something that is very expensive. So, this is not something that we have the chance to do a lot or very often. And so if we can transfer what we have learned about one domain to different objects so that we don't have to start from scratch, this also gives a great advantage. And one of the things that I'm particularly interested in is actually when the domain is simulated and the application is real data, which is very difficult to do, but I also think it will become increasingly important. So in the last 5 years in particular, we've seen a lot of deep learning. And so I wanted to tell you just a little bit about how deep learning is used in astronomy. The reason for that is very simple. It just works. But there are things that make some of the modern deep learning, by deep learning I just mean like anything that has more than one layer between input and output, particularly suitable for astronomy problems. So the first one has been convolutional neural networks. So convolutional neural networks proceed by looking at images. So they're really born to deal with image data. And so for astronomers, this is amazing. And then they have basically a built-in feature extraction mechanism. They go in and analyze little parts of the image and in such a way that they can extract meaningful, specially correlated features. This could be edges, for example. This could be corners. This could be correlation between different areas. A bit like, if you were looking at a picture of a face, you know that the most important information to recognize a face would be something like not just the single brightness of each pixel, but like the distance between the eyes and the distance of the eyes in relation to the nose and the mouth and so on. And so for us, again, when we look at a picture of a galaxy and we want to recognize a shape, you can see that something has the ability of understanding whether or not there are things like spiral arms is incredibly valuable. And so this has been really a game changer in many ways for astronomy. This is what I'm showing here is actually a different application, which is recognizing strong gravitational lenses. And gravitational lenses are like a really fun things, and are the fact that, if you have a large object, typically like a massive elliptical galaxy, like you have here in each one of these squares, then you may actually see light coming from a background source that, couldn't really go through, and so had to deviate because, of course, mass bends the space-time, and so it's not coming from a little circle around the lens. The geometry is never perfect, so it's very hard to see a full circle, but we can typically see things like arcs. And so these arcs are really cool because often the source in the background that is now being distorted in the shape of an arc is a very, very far away galaxy. And so, this is one way that we can basically amplify the signal from background sources. And that's why it's called lenses, like the same thing that a magnifying lens does, but just in this case, gravity is doing the lensing. And so finding lenses in, archival images is something that convolutional neural networks are really talented at. One more, generative adversarial networks. This is another super fun type of neural networks in which you actually put two networks competing with one another. One is the generator. The generator makes fake images, let's say, or fake objects. And then the discriminator is trying to look at this and say, okay, this is fake, this is real, this is fake, this is real. In fact, this whole algorithm was born for fraud detection. So what are astronomers doing? Do we really care about fake galaxies? Well, no, this is not our main application, but something that we really care to do is to make amazing simulations that resemble reality. And for that, we can use this network and train it until simulated galaxies don't look exactly like real galaxies, not just at the single object level, which is fairly easy to do, but at the level of an entire population. And then we can use the simulated galaxies to study real objects because we know for a fact that we're similar. Another thing that we have been able to do with these galaxy images that you see here in the left of this example is to upsample the resolution of the images that we have. So the amount of information that we can recover putting together a noisy image together with a GAN input in how galaxies should look like is more powerful than, like any algorithm that we have to remove noise, which is the deconvolved version that you see here. And these in practice correspond to enhancing our time at the telescope, so achieving a larger, stronger signal to noise ratio without touching the survey. So this is also amazing. And then let's see. The last one that I wanted to mention is recurrent neural network. These are also super fun. So in general, what happens when you have like an input and an output, and in the middle you have a neural network, is that, okay, you have layer, weights, okay, backpropagation, forward propagation, and in the end you spit out an output. But the output for different inputs are independent of one another. So in a recurrent neural network, what you do is that the network conserves the memory of previously given answers. And these previous outputs also become one channel of information. So they are particularly popular in, say, natural language processing, in which we can do things called sec-to-sec, which means like we have like a sequence of input that are processed together, and they generate a sequence of outputs. For example, when you're translating from one language to the other, you usually don't want to translate word for word. This doesn't give a good result, but being able to translate group of words or sentences at the time is much more advantageous. Or for example, let's say that I had fed one of these networks some biographical information about me, and then I asked the network to complete the sentence I was born in. And for the network to know that I'm talking about myself and complete this as easily, it needs to know what was the input of 4 or 5 words ago, and recognize that this was like the most important bit of information in order to influence its output. Now, what does this have to do with astronomy? A lot when you're talking about time domain events or transients. Say, for example, that in your data there is suddenly a supernova exploding. How are you going to see this in an automated manner? Basically, you want to have like a detection pipeline that tells you about something unusual that is happening. And this something unusual may not be something different from, sort of like pixel-wise from other ordinary events. It's just that the timing or, the behavior as a time series will be different. And the same could be like, the detection of like other unexpected events or, unexpected objects that we simply cannot model and so we cannot plan for, or even just, like the failure detection, something that you probably want to fix in real time. And so this is why they have, they have a bit less history than the other two methods, but they're becoming increasingly popular. Okay, now basically the last things that I want to share with you is the fact that I'm sure that, all of you have somewhat participating in the increased popularity of deep learning in the last 5 or 10 years. But even if some of these are relatively new, right? Like GAN, for example, generative adversarial network are from like 2014. The general concept and algorithm of neural networks has been around since the 1960s. So why did they suddenly become so popular? I think like one reason is that data has become bigger in many fields, but the other, I think, is just accessibility. And so let's see, how many of you have seen this data set before? You can put it in the chat if you know. Yep. Okay. All right, I'll give a minute while I prepare to do the same. And Yanis, I saw your question, so I will try to answer when I'm done with this. Okay, well, I guess we have at least 5, which makes it, yes, okay, very good, 6. So yeah, we are like over 10%. So what we're saying here is like, a classic machine learning data set, which is, like is based on the recognition of digits, and originally it was, from the US Postal Service, because, being able to automatically recognize zip codes was very useful in like sorting mails for, wherever it had to be sent. And so this is, like a classic intro level data set that is also used as a benchmark for when new methods are proposed. But what I want to say about this is that writing a neural network is something that has become incredibly easier. And so this is, what I wanted to show you. If I wanted to use, for example, these are like, in a way, simple images, but still image data. Like, each example in this data set is a 28 by 28 pixel image. And let's see, if I want to write a CNN to analyze this data set, I should be able to do this in about 10 lines of code. So I'm going to see if I can share this other thing, which is, let's see, hopefully I'm sharing the right thing. Do you see my Colab? Okay, thank you. All right, so Colab, by the way, I don't know if, I'm sure at least some of you have used it. So Colab is, it's short for like co-laboratory, so collaborative lab, and it's a free tool that is available to anybody with a Gmail account, where you can, for example, like run Jupyter notebooks, and they give you GPUs for free. In the free version, sometimes you can get something that is like not the fastest, or sometimes you can be like booted out of the system, but it's still like quite powerful. And so this is like, a tiny code that I wrote. Actually, I didn't even write all of it. Most of this is adapted from this source. And so let's see, what I'm doing here is that I'm importing the data set, which is, as several people in the chat correctly pointed out, is MNIST. And then I import in TensorFlow, which is like, the main package that we may want to use to build neural networks. And then this next cell right here, we are loading the data, we are reshaping and renormalizing, just because, these are image data, so you have an intensity from 0 to 256, and neural networks select them between 0 and 1. Then, I'm sort of like formatting the output, because, there are like 10 possible outputs, since I'm trying to recognize the digits from 0 to 9. And so I'm saying, okay, this is what my output will look like. And actually here, yeah, the process that takes a little extra time is just downloading the data. And we can visualize the first few objects. So here, these are just like the first 9 objects. So you can convince yourself these are just like little images that show handwritten digits. And here, how we build a neural network model. We're just saying it's a sequential model. So I'm just going to add layers. I have a convolutional layer, in which basically I'm taking a small filters and looking for like different combinations of features in my pixels. And then I'm pooling, which is just like a way I implement dimensionality reductions by averaging in like little blocks. This dropout things is just there to avoid excessive overfitting. Like, let's add a little randomization to my process. Flatten, just change the shape. And then I'm adding a dense layer with 128 neurons, and I'm connecting this to my last layer, which is the one that goes from 128 to the 10 classes that are my possible alpha. Now I'm saying, okay, you can compile the model. I'm going to have to define a loss function, and I'm going to have to say, okay, how I'm going to estimate the goodness of my results, which is through accuracy. So let's do this. And then this is how I fit the model. And so in model fit, I'm saying, okay, I'm only training for 10 epochs, which means, I will repeat my process 10 times, hoping to converge to a more and more accurate solution. And finally, I will evaluate my model looking at the performance in the test set. Okay, so, I chose like a training set, and then I'm going to see what happens. Now you can see this happening with me. Let's say I'm still on epoch 1 of 10. And if you go here to runtime, by the way, you can look at what I have, and you can see that I have selected a GPU as my hardware accelerator. And so this, once it starts, it goes pretty fast. And so in, 10 lines of code, plus some inputs, and about 10 seconds, I got to a point to like a CNN that has an error rate of just over 1%. Is it amazing? No, you can do a lot better. But given the resources that we have to use, I feel like that, like the availability of this, and I also like to think like the availability of this really worldwide and for free is something that, constitutes the real revolution of these fields. And so here I can just like get a random object 703, and then we can look at it. Okay, it's a 7. 7 is actually not the easiest object to classify. So let's see if we can predict it correctly. Yes, it's a 7. And like you can do this with a random seed. And so now we have a 4. And look, we are predicting it as a 4. And so I felt that, this is, in my opinion, what I really found was the biggest change between 10 years ago and today, the fact that basically nowadays, you don't need to write a neural network from scratch, and you don't need to have access to your own personal resources, but just like the availability and accessibility of these has really changed. So I guess this is the last thing I wanted to share with you, and tomorrow we can continue talking about the more practical examples. And so now I guess these last few minutes I can go back to the questions. So let's see. Yanis was asking before, does the trainer's bias will influence what these neural networks will produce? This is a great question. I would say there's always the possibility that even, like choosing algorithms, since some algorithms can only model certain type of relationship, plays a role. I feel like one way in which this can happen is the fact that we feed a learning set that is not representative to our domain set. And I think this is, I was considering actually including a discussion of the fairness of AI. If you guys want, like if we have time tomorrow, I can show you something about this. But I think that, for example, like this kind of algorithm have been used a lot in things like, like hiring decisions, with the expectations that perhaps they will make the hiring process fairer. But then it turns out that, if you keep feeding a learning algorithm, a lot of instances in which the people who are hired are white men, well, like the AI, of course, will inherit the same bias. And so I think it's definitely possible that the trainer bias will be retained by the models. And I feel like the clearest way in which this can happen is the fact that the learning set will not be a fair representation of the domain set of, in other words, like the set of objects that we would like to apply the method to. I feel like I would be more worried about this than about like just the relationship that can be modeled by neural networks. And I guess tomorrow I think we'll look at practical examples in which like your algorithm can say everything is nice, but you can still have biases that are a bit harder to see. Okay, let me continue. Amir, you were asking, can I show some cases the machine predicted wrong? Okay, so let me go back to that. Yeah.
Oh, I see.
Can you guys see the collab now?
Yes.
So, okay. Well, so I don't know how to give you the cases the machine predict wrong because, let me see. Because it's only 1% of the total. Let me see if I can, and I'm not that good at coding in real time. Let's see if I do. Let's see if we can find something in the first 100. So, la, 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 la. Yes. I hope that this is called white test. Yes, and then. I knew it. Okay, let's. Okay, and then. Okay, I'm gonna see if I can predict 100. I don't know if I was too optimistic about this, but let me see. Okay. Oh, I think I did something wrong here. Sorry, I'm confused. Like, I don't know where these are all predicted as 0 and 1. Okay. So let's see. You go away. All right, well, this runs, let's see. The 4 looks more like, if I don't know that I have, yes, definitely if you know, in this case, we are using the information that the only possible classes are numbers. And so, but this is, I feel like, fair, right? Because I think it's fair to introduce some like domain knowledge in a neural network. If we don't know, I think what we have to do is say, okay, we also have these other possibilities, or perhaps there is like an unknown class where objects that don't look like anything else should end up in. And let's see, yes, absolutely. I think that accent or yes, there are several biases. I feel like, you know, the one of like color that comes from names, for example, is, you know, that, you know, induces a discrimination that is based on race, and also discrimination that is based on gender is the most common. But definitely there are like, you know, like several other possible ways in which this could be biased. How long does it take to code up a reasonable prototype? And what resources would I recommend for a beginner? It's a very, very hard question to answer. This question from John. I feel like it's really like problem dependent. Perhaps, you know, tomorrow I will show you an example of the work that I did with a graduate student. And it took us, you know, we planned initially for like 3 to 6 months, and it took us 18 months. But I will try to at least, you know, show you what were a bit of the things that we got stuck on, which I feel like is not necessarily what we had anticipated at the beginning. And what methods can be used if there is so much noise that will become blur. I don't think that there is, I mean, like, you know, there are methods for noise reduction, but I think, and, you know, things that one can do is to experiment with some like image processing before feeding to a neural network. So this, you know, like the pre-processing, which is in general, like, you know, cleaning up the data and so on, is something that is quite important. Okay, so let's see. I think that we need probably to close up. I feel like here what is happening is that I'm misunderstanding what the whitest variable is. I don't think that this means like 0 and 1. So one thing that I can do is I will look back at this last set of questions and I keep this open, and I can start tomorrow's sessions if you guys are interested by going through some of these, and like I will have more answers that are ready in code to see like some examples that fail, for example. We can like reason together on why this is happening. And yes, I will be sharing the slides, and if you want to I can share this code too. Actually, like I can make sure that it's public, or just like post it somewhere.
Okay, maybe it's 1 o'clock and the questions are slowing down a little bit.
Right, but I promise I will,
yes, but
go back to those.
yes,
They will not go unattended. Or just,
yes. Good. Okay, so let me thank all of you for participating, and thank Viviana for a beautiful lecture. And I think actually somehow interaction is improving. So everybody's doing something right to make that work. And so I appreciate that. And we will see you all tomorrow at 11 o'clock. Bye-bye. Thank you.
Bye-bye.